You got it? I'll begin with a word of prayer. I'm going to begin with a word of prayer. So, dear Father, we thank you for this day again, Lord. I thank you for these students and for the break which is about to start. Let's pray to be with us today. Help us to understand the material that we're going over and not to get distracted by silly things. In your name I pray, Lord Jesus. Amen. Okay, so my goal today, guys, is, among other things, to explain to you what the real Jordan form is. So let's get to it. So if you have a vector space over the reals with a basis, suppose it's a finite dimensional vector space, then the first thing I'd like to point out to you is that that basis, beta, is also a basis for the complexification of the vector space. The proof of that isn't that difficult. Basically, you just say, okay, so like look at something in the complexification, which has the form x plus iy. All right, as I explained last time, why that makes sense. We explained how to construct that. And, well, if x is in V and y is in V, that means that I can expand both x and y in terms of the basis for V, right? So there have to exist real constants, x1 through xn, and y1 through yn, which give weights to form x and y as linear combinations, right? So this and that, I'm using the fact that beta is a basis for the vector space. Make sense? I hope so. I mean, beta is a basis, so you can expand x and y in the span of the basis, right? But then you just rearrange the sum, and what do you got? Well, you can pull a vj out, and you're left with this. This is a complex coefficient, right? Which is allowed in the complexification, which is a complex vector space, which takes complex numbers as the scalars, right? And so z is an element of the span over C of the same set of real vectors, beta. So the vector space and its complexification are united. They share the same basis. All right, that's a nice thing. So what that means then, right? What's a consequence of that? I can look at the matrix of T, right, with respect to the beta basis, and that will be equal to the matrix of the complexification of C with respect to the beta basis. And that makes sense to talk about that, right? On the one hand, we have T being a linear transformation from V to V. Over here, I have the complexification of T. I called it T tilde last time, but let me call it T sub C this time. Okay, so like T sub C is T tilde from last time, all right? So the complexification of T maps from the complexification of V to the complexification of V like that. So in principle, now in principle, if you look at the matrix of an endomorphism of a complex vector space, right, you should get an n by n complex matrix. But that's not the case here, right? If you're looking at the complexification of a real transformation, you still get a real n by n matrix. But this, it's true that this is going to be a matrix with real entries, right? It's a matrix with real entries, but it's found in Cn by n. This is important because this allows me to make the following definition. If T is an endomorphism of a real vector space, linear transformation from V to V over R, all right? And if the complexification, all right, T sub C, which is of course a mapping from TC, VC to VC, has complex eigenvalue lambda, let's say equals to alpha plus I beta, typically, and eigenvector, let's say V, all right, which of course is not equal to 0, such that what? Meaning what? What's that mean? That means T sub C acting on V gives me back what? What does it mean to say that the complexification has an eigenvector V with eigenvalue lambda? What happens? It just gives you back what? Lambda times V, right? Then what? We say T has complex eigenvalue lambda and complex eigenvector V. Now technically, those are not, technically if beta is not equal to 0, right? My definition is a little bit loose. I would allow a real eigenvector to be a special kind of complex eigenvector in this language, right? But the genuinely complex eigenvectors are the ones that come attached to complex eigenvalues with beta not equal to 0. If beta is not equal to 0, then it's an honest to goodness complex eigenvalue, right? And so that's what we mean by complex eigenvector. Now, a real purist in linear algebra, some of them don't like to even talk about these because it's some kind of, let's say, it's a hybrid. It's a hybrid. We're talking about a real vector space, but then we're talking about complex things. It's kind of a mixture of worlds, but it's a useful construction because it allows us to solve real problems using complex techniques. Let me show you how. So, remark. To find complex eigenvalues, what do? Just solve the determinant of the matrix of T with respect to beta beta minus lambda I equals to 0. Or if you want, you could put an x here. But the thing is, we allow lambda to be a complex number now. This makes sense. Why do I know that there exist solutions to this? Because remember, as I just showed you up here, this guy is the same as the matrix of the complexification, right? And the complexification of T is a linear transformation on a complex vector space. But complex vector spaces have how many the characteristic equation has n solutions, right? Because it's over the complexes that could be repeated, right? But the solutions are there, and that still makes sense, right? So we're just referring back to our theory of complex vector spaces when we do this. It just so happens that we can use the real matrix in this way. All right, now there's a theorem. If the dimension of V, the real dimension, of course, is equal to 2, and you've got a linear transformation from V to V, all right, with complex eigenvalue lambda equals to alpha plus I beta. All right, beta not equal to 0. Let's keep it interesting. And complex eigenvector V equals to A plus IB, all right, where A and B are real vectors. Okay, those are elements of V. Then the following. Let me write them out here. A couple points here. Number 1. Point 1. First thing we can show is that the conjugate, excuse me, V star equal to A minus IB. All right, this is the definition of the complex conjugate of a vector. You just switch I to minus I, and real stuff doesn't change. This is an eigenvector of T, of course, with, well, eigenvector of Tc. And hence, it's a complex eigenvector of the original transformation with what eigenvalue? It's the conjugate, lambda star, which is alpha minus I beta. That's point number one. Point number two. If you look at the set A comma B, this is a linearly independent subset of the given vector space V. Three, gamma equals to A comma B is a basis. I mean, that's kind of immediate from point number two, right? There's nothing shocking there. If you have two linearly independent vectors, it's a basis, right? But here's the interesting part, basis for V. And the matrix of T with respect to this gamma basis has the following form. Alpha minus, wait a minute. Alpha beta minus beta alpha. 4, T is the composition of a dilation and rotation, and possibly an inversion. All right. Let's prove it. So what are we given? We're given what? We're given that T sub C, right? Acting on what? A plus IB gives you back what? Alpha plus I beta, right? And then what? A plus IB again, right? Any of you Greek? Good. Then this should be okay. I have Greek friends. I'm like, did you write alpha or did you write A? And she's like, yes. I'm like, no. No. Alpha and A are different. So if you think alpha and A are different, then you should understand this. If you don't, well, this is really confusing, right? So this is just the definition of what? That V equals A plus IB is a complex eigenvector, right? Now we use the definition of the complexification, which is what? This is really just T of A plus I times T of B. That's how we defined the complexification last time. It just basically spits out the I and proceed as normal, basically. This over here we can multiply out. This is alpha A minus beta B, because I squared is minus 1, plus I times alpha A plus beta B. If you'll allow me a slightly atemporal proof, I would point out at this point it's immediately obvious why this is true. If we can prove that gamma is indeed a basis, right? Because once you have this, what does this say? We see T of A is what? Alpha A minus beta B, right? And this says that T of B is alpha A plus beta B. Thank you. Yes. Very good. And I should make those corrections over here as well. Alpha B plus beta A. So here I'm looking at the real component. Here I'm looking at the imaginary component, right? The way we constructed the complexification was to build it by a Cartesian product, right? Where the real component is one of the parts of the product and the imaginary part is the other part. So the only way you can have a pair of, a two-tuple equal, two of them, is when the first match and the second match, which here just means the real matches the real and the imaginary matches the imaginary. So I'm getting to equate this with this, right? And that with that. But then what? If gamma is the basis, right? So for gamma equals to a comma b, you see what we got? We've got t of gamma gamma. See what this is? This is the first column, which is alpha minus beta. This gives me the second column as beta. That's the first thing in the basis, and then alpha. Okay, so sorry, I got a little bit out of order here. We have proved 3 once we've proved linear independence of gamma, right? Does that make sense? All right, let's try to figure out the first thing actually. So how do I get knowledge? How do I get information about the conjugate? What I do is just take the complex conjugate of this equation. And if I conjugate this, I get t of a minus I times t of b is equal to alpha a minus beta b minus I times alpha b plus beta a. But then we just work backwards. All right? Go back to the complexification. This is the complexification on a minus ib is equal to alpha minus I beta times a minus ib on multiplying. That proves, so therefore Tc of the conjugate of v is equal to the conjugate of lambda times v conjugate. Which goes to show you number 1. The conjugate eigenvalue is also an eigenvalue of the complexification, and the eigenvector is simply the complex conjugate of the original eigenvector. All right. So that's number 1. 1 is done. To prove number 2, I would start with doing this. What can you tell me about the linear independence over the complex numbers of, if you look at this set v and v star, what can you say about that? Is that a linearly independent set? How do you know it? Well, yes. This is it's a set of eigenvectors for the complexification, right? With distinct eigenvalues, right? Because what? Lambda is not equal to lambda star, right? Because we assume that beta is not equal to 0. So you've got alpha plus I beta, alpha minus I beta. Those are not the same complex number. Those are distinct. Therefore, the eigenvalue vectors are linearly independent, as we proved on a previous day. Distinct eigenvalues give you distinct eigenvectors, linearly independent eigenvectors, right? So what? We're trying to prove that a comma b is a basis, right? So then what you got to do is some kind of math like this. So like v plus v star, what's that equal to? And what's v minus v star equal to? What's the sum of the eigenvectors? It's what? See what happens when you add v and v star? You get what? I heard it. 2a. And this gives us 2ib, right? So therefore, a is equal to 1/2 of v plus v star, and b is equal to 1/2i of v minus v star. And then if you take these, if you just consider c1a plus c2b equals to 0, right? What's that tell me? That tells me that c1 times v plus v star over 2 plus c2 times v minus v star over 2i is equal to 0. And if you just do a few more steps, you can easily prove it, okay? because we know that v and v star are linearly independent, so we can equate the coefficients. You can work it out, pull off a coefficient of v star, pull off a coefficient of v. So like just a few more steps here. This is c1 over 2 plus c2 over 2i v plus c1 over 2 minus c2 over 2i v star equals to 0. But by linear independence of v and v star, I get that the coefficients of that is 0, right? And you can easily solve those two equations and two unknowns to imply that c1 and c2. So this must be 0, this must be 0, and that does imply that c1 equals to c2 equals to 0. Consequently, a comma b is linearly independent, as I claimed. So it's a basis, and so my calculation in green up there made sense. All right? So what's left is number 4. Why is it that the linear transformation is a combination of a reflection and a, a rotation, a dilation, and possibly an inversion? Well, this you could rewrite as what? This is, check this out. This is like 1 over plus or minus the square root of, well, let me just write it this way. This is 1 over r. I'll get it essentially here. 1 over r times alpha over r, beta over r, minus beta over r, and alpha over r, where r is equal to what? Alpha squared plus beta squared, right? Now, check it out. So if that's the case, what's the, what if you multiply, well, how can I say this? You can argue then that cosine of theta is alpha over r, and sine of theta is beta over r, something like that. And what do you get if you calculate? Does that make sense? I mean, is cosine squared plus sine squared equals to 1? You get alpha squared plus beta squared divided by r squared, which is r squared over r squared, which is 1, right? The thing is, I might not be able to do this because if this actually has the form 1 over r, cosine theta, sine theta, minus sine theta, cosine theta, like I'm arguing, I'm not sure I can assign a thing. I might have to put a minus out front in order to make it work, is the thing. I don't want to get too far into the details here, but basically, to be fair, you have to put a plus or a minus out here, and maybe, or you could say r is plus or minus. I mean, and so the minus is the inversion case. If the determinant of this is negative, there's an inversion. It could be that the determinant of this is negative, I think. Wait a minute. No, it can't be. I'm an idiot. Let me just accept the math. There's no plus or minus here. It's just r. There's no inversion. I don't believe that for a second. No, I take it back. No. Look at this. The determinant of this is what? Alpha squared plus beta squared, right? That's positive. So, and r is positive because beta is non-zero. So what you're looking at, yeah, it's fine. I'm sorry, I talked myself out of that here just a second ago, but let me stop. So this is a dilation. It's a scaling by a factor, and this is a rotation because you can prove that it satisfies the condition for a rotation matrix. We'll talk more about that in the next part of the course. So if you're not familiar with that being a rotation yet, that's okay. I'm just trying to explain to you what the geometric meaning is of a complex eigenvalue. What it's saying is that your transformation's actually got some kind of rotation going on, and possibly a scaling, those two things, in 2 dimensions at least. Any questions? All right, so that solves one of our problems, right? If we have a, yes?
Why do you divide by 1 over r and divide
Oh, that is a very, very good question, Gwyneth, because I should, of course, multiply by r. Why? I mean, you guys are allowed to think for yourselves. I mean, I didn't forbid it. Yeah. Please do. I appreciate. I'm not. I mean, you know, we want to make math great again. I need many advisors. You know. Let's see here. Let's see here. I want to make math the way we remember it used to be. Sorry.
So like what era are we going?
That's important. I personally like maybe 1960 to 1970, something like that for math. It's pretty good. Let's see here. Look, so let me recap. Why did we need, why do you need this? Is because we do not like, I'm sorry, it will come back in a little bit. The rational canonical form is a drag, right? It was not fun. So for a real vector space, we'd like an alternative. And a good alternative, a standard go-to, is this real Jordan form. So I've already shown you if we have a complex eigenvector, which is one of the things that can happen, that corresponds to one of these 2x2 alpha rotation dilation blocks, right? What else could happen is you could have a complex generalized eigenvector. That could also happen. So let me just explain to you what's going on here, and I will just talk through it with you. It's a lot to try to write down, but I think you can understand if you read it together with me. I think having gone through what we just went through somewhat slowly should make this make sense, I'm hopeful. So, so this is basically the big theorem, which is that if you have a linear transformation of a real vector space, you can look at its complexification, right? This would, I maybe should have T sub C here. The complexification of T permits a complex eigenbasis. Generalized complex eigenbasis is the more general thing. If it happens to be complex diagonalizable, then it admits a complex eigenbasis. Then you don't need the generalized complex eigenvectors, fine. But generally speaking, you might need generalized complex eigenvectors to get the generalized complex eigenbasis for the complexification of T. But once you have that, that means you could put the complexification into so-called complex Jordan form, right? Now that's not a Jordan form for your original matrix, but when we'll talk about in just a second here, is you can take that basically, and through a systematic procedure, you can go back and find what's called the real Jordan form for your original real transformation. What I just showed you here, this 2x2 block that we just derived, that is the real Jordan form for T in the case of one complex eigenvector with complex eigenvalue alpha plus I beta. We already, that is the real Jordan form. That's the basic case of it, what we just did. See this? If we have a two-dimensional real vector space, blah, 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 just what we just talked about, this right here is the so-called real Jordan form for T. All right? What's the next step up here? By the way, I think the proof I showed you today is an improvement. It's an improvement of what's in my 2015 notes. Next case up, 4 dimensions, 4 real dimensions. That's how many dimensions you need to get a repeated complex eigenvalue, which has geometric multiplicity 1, but algebraic multiplicity 2. In other words, you only have one complex eigenvector, not 2. That means for the complexification, you have to find a generalized eigenvector of order 2 to complete the complex basis. And anyway, if that's the case, so what you're going to have is a complex chain. You get V1 equals to A1 plus IB1, a complex eigenvector. A generalized complex eigenvector, V2 equals to A2 plus IB2. The A's and the B's are real vectors, okay? And it satisfies the chain condition, T minus lambda I, that's identity, times V2 equals to V1. That makes V2 a generalized complex eigenvector of order 2, right? If you do that, then with respect to this basis, A1, B1, A2, B2, you get this matrix. That's the real Jordan form. In the case you have a repeated complex eigenvalue, and you actually have one, in this case. Here's the proof. The proof is really, I'll let you read it, but the proof is nothing more than what we did over here, just expanding this out into A's and B's and equating the real and the imaginary coefficients and using what's the definition of a basis for a matrix linear transformation. Like, I just basically multiply this out, and then I have this is the real part, that's the imaginary part. That's a typo. There's a plus right here, guys, obviously. Sorry, what idiot wrote these? And anyway, so this gives you, eventually you get that T of A2 is equal to that, and that gives me that T of A2, the coordinate vector, that's 1, 0, alpha minus beta, which is this, 1, 0, alpha minus beta. And then if you look at T of B2, you get B1 plus beta A2 plus alpha B2, and that gives you 0, 1, beta alpha, which is that one. So that's where these mysterious ones come from up here. There's a really cool pattern. There's a way of understanding this. Let me show you. Well, okay, fine. I'll get to it eventually. This is the complex Jordan form I was talking about. I don't really care much about that. We're interested in a real matrix, but this is the complex Jordan form, which corresponds. Here would be the complex Jordan form for a three-peated. If you had a three-chain of generalized complex eigenvectors for a given real transformation, they always come in conjugate pairs. See that? Now, what would the real Jordan form look like for that? Here's the real Jordan form for the case of a three-peated complex eigenvalue alpha plus I beta. You got this block, the same block again, the same block again, and then these ones on the super diagonal, right? Like so. There's a pattern here. This is what it is. What this means, this is the so-called tensor product. We'll talk more about this in a future lecture, not too much today, but basically what this means is you take this matrix, right, and you stick it as a multiple of it here, 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 and here. It's a new way of multiplying matrices to get new matrices. This will give me a 6 by 6 matrix. So if you go back up here a bit, what just happened? I pressed something and it just went. So let me try to see the pattern if you guys can see it with me. So see, this times that puts this 2 by 2 block in the block diagonals, right there, there, and there. It puts 0 copies of them everywhere else. All right? So that's just where the alpha and betas are coming from. This puts the identity matrix here, 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 and here, but multiplied by 0, so it's not there wherever there's 0, right? But it does put an identity here and here, which is exactly what you got up here, right? Check it out. You got a 0 block up here, identity matrix, right? This is the fundamental nilpotent thing from a 3-chain, right? This is the same thing we saw in the Jordan form has this ones on the superdiagonal if we have a 3-chain. That's a 3 by 3 Jordan block. And so if you wanted to look at what if you had a 4-chain of generalized complex eigenvectors, you can see the pattern. You just tensor product this with the identity and this with the nilpotent, the standard nilpotent thing of order 4. This is sort of your canonical nilpotent order 4 matrix. You power that 4 times, you get 0. But the third power is non-zero. The third power of this matrix has a 1 just up here. So you can start to see the patterns if you look at these for a while. Here's an example, whatever. These are the examples we should look at. So here, for example, let's just be more explicit. This 4 by 4 matrix, if I look at it, I see that this is in real Jordan form, by the way. Here's a 2 by 2 Jordan block, because this is a rotation dilation block. This tells me that the complex eigenvalue is 2 plus 3i. In fact, 2 plus or minus 3i are the complex eigenvalues. But you see, if we get the plus 3i, we don't need the minus 3i, because all the information's just in one copy. If you look at the v star versus v, they have the same real vectors. They both have vectors A and B in them. Just the other one has minus B. So we get all the data we need from just one complex eigenvector. But this over here, well, that's what we were talking about before. That's just a eigenvalue 5 repeated, right? And one eigenvector, one generalized eigenvector order 2. So the combination of these two things is what's known as, like this, the real Jordan form. You can always take a real transformation on a real vector space and find a basis which puts the matrix of the transformation into real Jordan form. All right, it's totally general. This one here, what would this be? That's plus or minus 3i, right? Because the zeros. And looks like there's a block here, right? So it's complex eigenvalue plus or minus, well, let's say 3i repeated twice, right? There's only one complex eigenvector because we got this, it's got the Jordan block thing going on. And then down here we have real eigenvector, eigenvalue 5 repeated twice, and the geometric multiplicity is 2. I mean, that's an eigenvector. That's going to, it's like, let's see here, 1, 2, 3, 4. E5 and E6 will both be eigenvectors with eigenvalue 5. So anyway, it's if you're already given a matrix in Jordan form, once you understand the theorems I'm telling you, it's pretty easy to read off of them what the eigenvalues and the geometric and the algebraic multiplicities, as well as other things like the characteristic polynomial, the minimal polynomial, all of these fun things. So that's it. We don't know about orthogonality yet. That's kind of next on our list of things to do. Actually, it's not next. What's our next thing? Oh, yowzers. Thank you. I'll take both lights. All right. I have spent a lot of effort to try to explain to you this thing called the Jordan form, right? Why did I do that? I mean, I guess I've buried the lead, right? I should start with the why, and then you guys would care more, right? Oh, well. What can I tell you? It's too late. I mean, if I could have a mulligan on this part of the course, I would tell all of you to go read my eigenvector chapter first, and then to attempt the monstrosity, which is the chapter on structure of linear transformations in Curtis, right? My eigenvector chapter might help you prepare for the theoretical onslaught, which is that chapter in Curtis, right? It took me time to digest that chapter, right? And it's not at all easy. There are many easy things in it, but the totality of it, man, it's pretty beautiful. Can I erase this? I'm going to. So why do we do this? Well, the reason we do this, the reason I feel, because I could make my life easier. I could say nothing about canonical forms in this course. No other instructor would argue with me about that. Most people have said, oh, it's too hard to teach. Can't do it. It's too much for the undergraduate course. Well, fine. But the reason I talk about it is because it allows you to solve problems that you could just not really decently solve otherwise. Here's an example. There's an identity. The exponential of the, well, oh man, I got to explain something first before I can explain this identity. Definition, e to the a is equal to the sum, k equals 0 to infinity of a to the k divided by k factorial. Let me write out the first few terms. You're like, what? No! This is linear algebra. I am safe from series in here. What are you doing? You're a bad person. No, don't bring series into this course. Sorry, it's too late. It's been written. What's been written can't be unwritten. You can prove that this series converges for arbitrary matrices. You can give a notion for the convergence of a series of matrices, all right? Don't worry, I'm not going to get into that. But this is the so-called matrix exponential. What are its properties? How about this? E to the 0 is equal to I. Well, that's kind of cool, right? And if AB is equal to BA, then you have this also, e to the A times e to the B is equal to e to the B times e to the A. You can prove that. Don't worry, I'm not going to do that to you today. What does this tell us? Well, how about this? Then if we have, notice, so A and minus A is of course equal to minus A times A, right? They commute. So what happens if you look at e to the A times e to the minus A? Oh, I'm an idiot. More than this. This is equal to e to the A plus B. Sorry, I buried the lead again. Yes, this is e to the A minus A, otherwise known as e to 0, otherwise known as I, right? So therefore, e to the A inverse, as a matrix inverse, is equal to e to the minus A. That's pretty cool, right? Don't get too carried away, though. If A and B don't commute, suppose A and B don't commute, then it's something like this. E to the A plus B plus 1/2 commutator of A and B plus 1/12 the commutator of A with the commutator of A with B plus 1/12 the commutator of B with the commutator of B with A plus higher nested commutators. Now, I really have to put a plus or minus here, and this plus or minus is not like a plus or minus that has to stay there. It's a plus or minus that's there because I simply don't remember the sign of the formula past that order. This is the so-called Baker-Campbell-Hausdorff relation, the BCH relation. Baker-Campbell-Hausdorff relation. This lies at the heart of all modern physics. This tells you the relation between the Lie algebra and the Lie group. It's a very important formula. Anyway, so my point is matrix exponentials, they look like they're the same, but they're not quite the same, right? Okay, so check this out. If I have e to the diagonal matrix D, where D is equal to let's say D1, D2, Dn, then what's d to the k power equal to? Think about it. It's the diagonal of what? D1 to the k, D2 to the k, and so forth, right? If you take the kth power of a diagonal matrix, it's the diagonal of the kth powers of the diagonal, right? Agree? I hope you agree. Yep.
I'm just confused why it goes from 1/2 to 1/12.
Oh, that's complicated. No, that's not something you want me to derive or to be asked to derive.
So does this keep going just on with 1/12?
Oh, no. It does other things. It's not something I know. I just happen to know they're 12ths. I've worked that out. I'm hoping actually to derive this in one of my Monday, Wednesday, Friday sessions with some students I'm working with. We're hoping to one of the things I'm hoping to prove is this relation. So I might have a better answer for you in a few weeks. Anyway, what's e to the d? It's the sum, k equals 0 to infinity, of d to the k over k factorial, right? But what is that? That's exactly the same as the sum, k equals 0 to infinity, of like d1 to the k over k factorial. What is this? Block, one by one blocks, but yes. It's a diagonal matrix. So, the point is, everything else is 0. So like d to the k, this is just d1 to the k, dn to the k, zeros elsewhere. So this becomes that. What are these, though? You guys know your calculus too. This is what? E to the d1, e to the d2. It's just the ordinary exponential series. In other words, the exponential of a diagonal matrix is the diagonal matrix of the exponentials. Pretty neat. So, okay, here's an identity which happens to be known. The determinant of the exponential of A is equal to the exponential of the trace of A. Here's a claim. I submit to you that's easy to prove in the case that A is diagonal. If A is diagonal, what do you get? Suppose A is equal to D, right? Where D is diagonal, what you got? You got the determinant of the exponential of D, which is what? The determinant of e to the d1, e to the d2, and so forth, right? You guys know how to calculate that determinant. What is it? Like that, right? That's e to the d1 plus d2, dn. Hey, what's that? That's the sum of the diagonals. That's the trace of D. So this identity is easy to prove for a diagonal matrix, right? I haven't told you all of the matrix exponential secrets yet. There's another thing. It behaves really nice under similarity transformations. You can prove the following. You can prove that P inverse e to the a p is equal to e to the P inverse AP. This is another identity which is known for the matrix exponential. Pretty cool, huh? I think it's cool. I don't know. You can disagree. So, what do we know about any matrix? We know any matrix can be put into Jordan form. Right? Now I'm going to keep it real here for a second. So suppose, because I don't have much time, eigenvalues of A are real. I suppose we could just do this calculation over the complexes if we wanted to, though. This stuff makes sense for complex exponentials. But just to be more friendly, let's suppose the eigenvalues are real. Then what do we have? We have that there's a Jordan form, J, which is equal to P inverse AP, right? And what did we learn? We learned that the Jordan form, well, before we talked about the Jordan form, we talked about the Jordan decomposition, which is that J is equal to D plus N, right? Where this is diagonal, and this is nilpotent, right? So, what if I try to calculate the determinant of the exponential of A in view of this? Well, it's a determinant, right? So I can do a similarity transformation. It doesn't change anything. This is the determinant of P inverse e to the AP. But then I can bring the similarity transformation inside the exponential, right? Which is what? E to the what? This is P, this is J, which I'm going to get straight to the point. That's D plus N, right? Do the diagonal and nilpotent parts of the Jordan decomposition commute? They do. That was part of the theorem. Which means we can rewrite this as what? E to the D times e to the n, right? That was part of our Jordan decomposition theorem. The diagonal nilpotent pieces commute. So then what? Well, Determinant of the product is product of the determinants, all right? So we get determinant of e to the d. Hey, we just already worked that out, right? And we got determinant of e to the n. So what's this is what? This is e to the exponential of the trace, right, of d. And then all we need to do is show that the determinant of the nilpotent piece, the determinant of e to the n, is in fact just 1. I'm probably out of time. Oh, yeah. Let's see here, maybe we can do it. Now, of course, the trace of d is what? That's the trace of a, right, by similarity? Oh. What's that? Oh, don't talk to me. Here. I mean, n to some power, right, is equal to 0. So e to the n is what? It's like I plus what? Plus n plus 1/2 n squared plus dot 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 plus 1 over, k to the minus 1, n to the k minus 1. If you look at the details of this, it's all super diagonal stuff, right? Because this is not just any n. I'm talking about the Jordan block ends, those things we were tensoring with a few seconds ago, with the ones on the super diagonal, right? So powers just move the super diagonal up until you finally get to the one in the upper right-hand corner, and then that goes off the chart, and then you're to 0. That's how the powers of these n work. So this is all super diagonal stuff. In other words, what I'm trying to say is that this matrix looks like 1s down the diagonal, and then stuff up here. So the determinant of e to the n is 1. And there you have that identity for arbitrary matrices. In fact, this argument can be extended to the case that the eigenvalues are complex with not much comment, really. Now, if you look at my notes, I have vastly different proofs of this identity, which don't use the Jordan form. And you can see what's required to prove this without the Jordan form. Yep.
Should that keep plus 1 or minus 1? Should that be
Oh, thank you. Yes, definitely factorial. But that's, there. I don't know what that is. It's part of making math great again, though. It's 53. Yeah, I know. But